Okay, well, I'd like to thank the organizers for inviting me to speak. And I'd like to promise the chairman, Monica, that I will attempt to respect the timekeeping and tell you about Quantum Monte Carlo and a little bit about the method and an application to the catalyzed water-gas shift reaction on platinum. This reaction is carbon monoxide and water to produce hydrogen. Just a little bit of a map. Clermont-Ferrand is about 300 miles south of Paris, and just to the northwest we have some volcanoes which we hope are extinct. I'm going to report mostly results of a large supercomputer allocation in which my collaborators Tapio Rantala of Tampere, Finland, was responsible for preparing the input wave functions for Quantum Monte Carlo. And we need a very high level wave function for the molecular active site, MRCI, because there's going to be bond dissociation involved. And this will be embedded in a periodic system represented by plane waves. Rajesh Sharma was postdoc on the QMC, and he's now working in the Punjab in India. I'm going to follow this outline. The first item is just a euphemism for Hartree-Fock with CI, so I don't think for this audience I need to detail it. I will present to you how Quantum Monte Carlo works, which is in 2 steps. And the purpose of the first step, the variational Monte Carlo, will be illustrated, and the objectives of the diffusion Monte Carlo step will then be detailed to show how we obtain a fully correlated ground state after equilibration, and how the systematic error there may be is due to fixed node or fixed phase error in the trial wave function, hence the idea of having a good quality wave function for the back part of it, the molecular cluster which is reacting. We apply this to metal catalysis and have validated it by a hydrogen dissociation for which there are reliable experimental measurements. And the water-gas shift reaction is number 2, where we investigate the first step where carbon monoxide is pre-adsorbed and is attacked by water before the molecule dissociates completely, and finally produces hydrogen. So now I'm going to talk about the stochastic methodology and particularly apply it to solid state methods for electronic structure and properties. The key point is that the time-dependent Schrödinger equation is used, and this can be transformed into a diffusion equation for diffusion Monte Carlo, as I will show in the next few slides. Now, catalysis is really with the objective of reducing activation energy. It so happens that the water-gas shift reaction would be difficult to conduct without a catalyst at all because of the polarity of the isolated carbon monoxide molecule, which is contrary to the electronegativity of the atoms. And we really need a polarized carbonyl adsorbed on the catalyst for the reaction to go. So here is the result and references. We calculated the barrier for this first step in the reaction, which is like an SN2 reaction where water attacks a pre-absorbed carbon monoxide on a hollow site of the compact platinum plane. And we represent a small molecular part of it, 2 platinum atoms, one which is coordinating the hydrogen coming off the water molecule, and the other one which has the pre-absorbed carbon monoxide, which is accepting the OH. The barrier for this is more or less exactly 17 kilocalories per mole. We've had it published in a kind of summary paper in IJQC, and we're currently revising a very much meatier paper for JChem Phys. This is the cover, which is a representation of Azuro, the water spouting dragon, to represent the fact that hydrogen, when it burns, produces water which we can recycle. And we will see later that the water associates to 1 platinum before attacking the CO in the hollow site. Now then, the accuracy we're aiming for is so-called chemical accuracy. So we are well within it in this barrier, which corresponds to measured effective activation barriers, which are 17.1 kilocal, and we're at 17.2 with error bars of 0.2. So I said I wasn't going to talk to you about Hartree-Fock with CI. In the stochastic methods, the basic object is called a walker by analogy with the random walk. And it's a set of instantaneous particle coordinates in real space. And it defines a configuration. And the distribution of configurations will be used to represent an electron density. The stages of the method are choosing a trial wave function which should be pre-correlated. Full CI has been developed for this by Alavi and co-workers, and selected CI by Cafarel in Toulouse. The second step is to optimize the parameters in this wave function and update by propagation in small time steps. The electron-electron cusp can be put into the basis. There has been successful writing of this basis into VASP by Alavi and Kress. And post-Hartree-Fock methods have trouble describing the cusp. The variational Monte Carlo gives an intermediate quality of the wave function with typically up to 60% of the correlation. And what we will be doing is fixed node diffusion Monte Carlo, which can get up to 99%, say, correlation. And what we use is a Jastrow factor, which is a distribution, which is a description of the Coulomb hole constructed with a polynomial explicitly in interparticle distances with arbitrary coefficients, which are optimized in the variational Monte Carlo step. So you need the electron-electron distances, instantaneous values, as a polynomial, the electron nuclear distances and pairs of electrons and a nuclear. The three body terms are actually very important. And the variation on Monte Carlo calculates an expectation value where you can factor out a so-called local energy and use the Monte Carlo method for evaluating integrals in the probability distribution, which is sampled and gives an accurate expectation value for the energy eigenvalues which correspond to this local energy function. The way the diffusion Monte Carlo works is by replacing the time variable by IT, the imaginary time, in the time-dependent Schrödinger wave equation. And what you get is a diffusion equation with a target energy eigenvalue, which is updated. And since all the excited states have a time evolution which is exponential, a negative exponential, they will fade out, and this will produce an exact ground state which is fully correlated in the limit of an infinite number of small propagations in imaginary time, which is in fact treated as a time variable. So how do you know where to stop? The error, if it's statistical error, decreases with 1 over root of the number of steps. And usually if the error is purely statistical, the ratio of error in standard error gets smaller and smaller, and you would stop when it's about 1/10. And this, to give you an idea, would be about 1 million core hours time to solution for a cell of 700 electrons. DMC is not necessarily variational. The convergence is quadratic, and it may go to subvariational values. However, there is a transformation to make it variational, which involves a slightly modified way of choosing the time step due to causula. Now, what is the fixed node approximation, which is a possible source of systematic error? You need to use the product of your trial wave function with the updated set of configurations to give the current guess density, because otherwise you have nothing which imposes the fermionic antisymmetry. And it may, if you do not do this, it may go down to a lower Bose state. Now, the software we've been using is Casino, which I'm not going to detail. The distributions I've been talking to you about to represent the electron density are independent, and you only need to average the results rather infrequently. So the code is almost ideal in scaling to 4096 cores, and then you suddenly get hit by the volume of your data, which in this case was rather large compared with the RAM on the processors, because we used a 5-layer platinum slab with our water and carbon monoxide active site on it, which is 1440 electrons, and we found it not easy to reduce the size. This was 64 platinum atoms, and we got for the application to hydrogen dissociation, which has been fitted experimentally to 6.2 kilocalorie per mole by an empirical DFT method, a value of 5.4, which is within the target standard error. Previous work was comparing hydrogen dissociation on copper, which is actually quite difficult to treat because of the 3D electrons. It has been published in this work with Katarina Dobloff-Deer. And the advantage of using this benchmark is that it can be compared to accurate molecular beam measurements. And there have been several similar validations since. And afterwards, in 2018, we moved to the reaction we were really interested in. So we are limiting our model to a planar approximation, whereas it's known that close packed planes may rearrange. And we're also obliged for the CI to limit the size of the active site to one which contains 2 platinum atoms. I should say the platinum is not all electron. It is represented by a pseudopotential with Z equals 60. That is to say 18 valence electrons per platinum. So this is already quite big of a molecular system with, one platinum atom to coordinate the carbon monoxide, which is pre-adsorbed, and the other to coordinate the hydrogen coming off water. So this is a little bit of a recap. I've said the carbon monoxide is in a hollow site. It's not the water. The water oxygen attacks this carbon monoxide, which is pre-adsorbed. Note that it couldn't do it for free carbon monoxide because the excess carbon charge would be positive. We've used the embedded cluster strategy. We could use, we have previously used exponential type orbitals with complex exponents, which can be directly expressed after Fourier transform in plane waves. In any case, the wave function is going to be complex because we don't have an inversion center in these slabs. And you could also make the Jastrow factor complex, which allows you to shift the nodes during the variational stage. We've tried this. It doesn't actually give you a major improvement. It gives you a slight improvement. The mechanism is a radical mechanism with partial charge. Here is the transition state for the step we've been interested in. So the hydrogen coming off water is being linked to a platinum atom at the origin. The water oxygen is beginning to attack the carbon from carbon monoxide, which is in a vicinal hollow site. Seen from another angle, we have the water plane illustrated and carbon monoxide bond axis. The cell is expanded in terms of the number of K points. Now, obviously, those of you who've done solid state work will know that this is used for the reciprocal space for paving the Bridle-Line zone, and that DFT calculations don't converge until you get to about 16 or more K points. However, in quantum Monte Carlo, you multiply the size of the cell in real space. And so we could only fit in the memory a 2x2 cell and needed averaging techniques called twist averaging to compensate for this finite size. We had previously tested the pseudopotentials. We tried a 10 electron pseudopotential for platinum on a molecular reaction between the platinum dimer and hydrogen, which is known to go through a rectangular transition state and form two PTH molecules. With the 10 electron pseudopotential, we had 5 kilocalorie per mole error in the formation energy and could only get down to below 1 kilocalorie per mole with the pseudopotential I told you about initially, with Z equals 60, coming from the Stuttgart group, with a little bit of adaptation for converting the effective Cornell potential they produce to a pseudopotential with the norm conserving property which is required for quantum Monte Carlo. And then we got below 1 kilocalorie per mole error. And we had a preliminary study to see whether in the water gas shift reaction after adsorbing CO, you dissociate water completely or not. And we got a higher barrier, significantly higher barrier, for the complete dissociation of water. The transition state geometry is now obtained using QMC force constants at the variational Monte Carlo level. We previously used DFT geometries, but they're open to criticism, even though they're not very substantially different from what you get with QMC force constants. However, we have preferred to have in this study the QMC force constant going to a saddle point geometry. And so we get more or less to the end. We've got a barrier calculated by QMC for this planar model of PT111, which is 17, and the observed effective activation barrier is 17.1. What we would like to do in the future is completely kill off the hydrogen dissociation benchmark. This is in work in progress. And then branch out to reactions of industrial import. A challenging one is nitrogen plus hydrogen in the synthesis of ammonium. And now I have to thank the research team, which is mostly an experimental physicist team studying surfaces and interfaces at the Institut Pascal, and Price for computational resources, first in Spain, and then on Irene at the Sierra near Paris. That's if there are questions. I've now finished. Thank you for listening.
Thank you, Philip. And we have a question from Hugo. So could you please check your chat and answer this question?
Well, I can ask it orally if you hear me.
Okay.
I can't see the...
No, don't worry, Philip. This is Hugo asking a question.
If I say stop share, I can see you now.
Okay, well, I can. I would like to ask you a question about your VMC calculation, that you showed that the expectation value, you write it as a product of a density probability times a local energy. Now the local energy becomes infinite whenever the wave function has got a node, because you divide by psi. So occasionally the local energy can be infinite. Now it's multiplied by a density probability, which is proportional to psi squared, which is also zero, becomes zero in those nodes. Technically, you have a 0 times infinity. I mean, do you ever encounter numerical problems?
This is a very good question, because in fact, if you expand your wave function in Gaussians, then near the nucleus you have terrible oscillations. And so we made a study of the local energy with Peter Reinhardt, who you know, and we published a paper on this aspect, which shows that for the atomic part of the wave functions, the atomic orbitals which you're putting into your LCIO, you definitely need smooth functions. They have to be derivable twice without these problems. Now, the question you're asking about nodes outside is a subtle one. I think that what happens is that the whole expectation value goes to 0. I will, there is a proof of this. I will investigate and communicate it to you.
Okay, thank you.
Thank you. Thank you, Philip, for an interesting talk. And